In this lesson, we're going to see how we can combine functions in a very similar way to how we combine numbers. For instance, we can apply operations to numbers like adding, subtracting, multiplying, and dividing them. And it turns out that we could do the same thing with functions. So let's say we're given two functions called f of x and g of x. Sometimes we'll be asked to come up with a combination of the functions called f plus g of x. Notice that all that means is that we're going to take f of x and add to it g of x to get a brand new function. The same thing is going to occur with subtraction and multiplication and division. And so if we were to ask to find f over g of x, or to divide or to find the quotient of f and g, sometimes the name of the function would be referred to as f over g of x, which simply means to take f of x over g of x. One thing that's important to recognize here, though, is that g of x is not allowed to be 0 because we can't divide by 0. Dividing by 0 makes a number undefined, and therefore we'd have to find out what values of g of x makes the denominator 0. Let's try an example here. If we're given f of x is equal to 3x minus 2, and g of x is equal to 2x squared minus 4x, how can we find the difference and the quotient of f and g? So let's start with the fact that we're trying to find f minus g of x. Now just recognize that that means to subtract the two functions that we're given. So if we subtract f of x minus g of x, we're just going to put each function in their own parentheses, recognizing that 3x minus 2 is the quantity of f of x, and 2x squared minus 4x is the function g of x. Now I have to put them in parentheses because if we're subtracting, I need to make sure to distribute that negative to both terms, which now allows me to combine like terms. I only have 3x and 4x, which are like terms. So that means that we have negative 2x squared plus 7x minus 2. Therefore, f minus g of x is the brand new function negative 2x squared plus 7x minus 2. So let's take a look at how we can find f over g of x, or the quotient of f and g. The quotient just simply means to take f of x and divide by g of x. Well, same idea. We want to separate by putting in 3x minus 2 to the numerator and 2x squared minus 4x to the denominator. Now, technically, that is it. That is my quotient of the two functions. But because of this extra criteria where we need to make sure that g of x does not equal 0, we need to find all the locations where the denominator will be 0. So we should factor the denominator. And notice that by the zero product property, the denominator is equal to 0 at x equals 0 or at x equals 2, which is why we simply state the restrictions on the domain that x cannot be 0 and x cannot be 2. We're now asked to simply find f minus g of 3. So notice in order to find f minus g of 3, notice that that's the same way that we did f minus g of x, except we're told that the x value is now 3. So we could simply plug 3 into the function of f to find the output, plug 3 into the function of g to find the corresponding output, and then subtract the two outputs. But it turns out that because we've already found f minus g of x is this new trinomial, we could actually just replace x in this new function, f minus g of x, with 3 and simplify. 3 squared is 9. Multiply each of those separate quantities to get negative 18 plus 21 minus 2, which gives me a final answer of 1. So notice that anytime we're evaluating combinations of functions, we're simply combining functions and then evaluating at indicated inputs. Now there's one more operation that doesn't actually make sense when it comes to numbers, and that's called composition of functions. This operation has a notation of being f of g of x, and to compose means to bring together or to combine. So a composite function is really just combining or bringing together functions to where we've got a function within another function. And so to demonstrate this, we're going to look at an example from the real life here. We're going to look at an actual application of what we mean by composition. And that's going to be a road trip. So let's think of a road trip and recognize that oftentimes one quantity is a function of a second quantity that in turn depends on a third quantity. So think about us taking a road trip and wanting to know the cost of the car trip. Well, obviously the cost of the car trip is going to be dependent on how much gas I use, because I have to pay for the gas, and that's what's going to indicate the cost of the trip. So the cost of a car trip is a function of the amount of gas I consume. But how much gas do I consume? I'm obviously going to consume a lot more gas in a Prius or in a Dodge Ram truck than I am in a Toyota Prius. So notice that the amount of gas that I consume is a function of the number of miles that I've driven. Okay, because notice that if I drive 40 miles, that's going to be a lot less money than if I drive 700 miles. So let's start thinking of this as a composition of functions. Let's call machine G the function that describes the amount of gas as a function of distance. Okay, which means I drive 200 miles, and this is the amount of gas I use. So if I drive 200 miles, I use 5 gallons. Or if I drive 200 miles, I use 10 gallons. So that means we're going to start with a distance, figure out what the amount of gas is that I use, and that is going to indicate g of x. So my input is x, my output is g of x, or rather my input is distance, my output is the amount of gas. But now we want to create another function. What if I tell you, now that you know the amount of gas, what is my total trip going to cost? So notice that now machine F is going to tell us the cost of my trip as a function of the amount of gas, because maybe I know that every gallon of gas is going to cost me $2.89. So notice that the amount of gas is going to be the input to another function. So I'm now putting a function into another function, and I'm going to output the cost of the trip, which is f of the input. The input just happened to be another function. This is an application that indicates why we would care about a composition function. It's basically saying, how could I take a function and plug it into another function? So I can now find the cost of my trip directly simply by knowing the distance that I'm going to travel. This is called a composition function. So let's look at the notation. The composite function is referred to as f compose g of x. So notice that this left side, this symbol right here, instead of being a plus sign or a minus sign, which would be a sum or a difference, we would say f compose g of x. But a better way to actually physically work through this process is to think of it in another form, to where we write this as f of g of x. So notice in this case, let's do an example where f of x is 2x plus 4, and g of x is x squared minus 3x. So let's start by finding f compose g of x. Notice that f compose g of x means the same thing as f of g of x. So notice that g of x is x squared minus 3x. So the first step is just to recognize what the inside function is. So the inside function is x squared minus 3x. And now notice that that's the input that I'm plugging into the function f. So I'm going to take that whole input and put it in for x in the function named f of x. So if you see here, we've got the function f of x squared minus 3x is the same as 2 times that input plus 4. Distributing gives me 2x squared minus 6x plus 4. So to take f compose g of x means to take g of x and put it into the function f. Let's look at how that differs from the reverse direction, g compose f of x. Notice that this now says to take f of x and plug it into g. Well, f of x is 2x plus 4. So why don't we first write this as g of 2x plus 4. And now realize that we're taking 2x plus 4 and plugging it in as the input to the function named g. So notice g of x is right here. G of x is x squared minus 3x, and because there are two different locations where the input of x is, I'm going to take 2x plus 4 and plug it into both inputs in the function named g. G of the input of 2x plus 4 means to take 2x plus 4 squared minus 3 times 2x plus 4. And now it's just a matter of expanding. Notice that 2x plus 4 quantity squared means to multiply that binomial by itself. We can then distribute to get 4x squared plus 8x plus another 8x plus 16. And then over on the right side, we simply distribute the negative 3. Now we're able to combine our like terms, and notice that we get a brand new function, 4x squared plus 10x plus 4. The most important thing to note here is that f compose g of x and g compose f of x are totally different functions. So notice that we can see that by doing both of them separately, we're going to get those two different functions. Now I'd like to use that prior result in order to find g compose f of negative 2. So notice the only difference here is that now, instead of just keeping the function in terms of x, I'm being told that the input is now negative 2. So I do have an option again. I could calculate the output for f of negative 2 in the original function and find out what that output is. That output would then become the new input to the function named g. But there's an easier way to actually do this because we already know that g compose f of x is the function 4x squared plus 10x plus 4. So why don't we just take negative 2 and plug it into each of the x coordinates in that value. We now get 4 times 4 minus 20 plus 4, which gives me an answer of 0. So notice that composition of functions is going to be one of the most important types of operations, aside from adding, subtracting, multiplying, and dividing. But notice the process that we use in order to find compositions is by taking a function and putting it into another function.